All you people out there in internet land. So plate tectonics. So on the surface of the Earth, you have, and if you look at the bottom of 211, you'll see the crust, and then the upper part of the mantle, the area collectively known as the asthenosphere. So that is kind of floating around, almost imagine it, on the magma underneath. Now, there are a bunch of different plates, so it's broken up little pieces that are floating around, and they're interacting with one another in different ways. So that's really the first part of the notes here. How are they interacting with one another, and then what is the environmental consequences of those interactions? Okay? What? Earthquakes, volcanoes. Who said they were hot?
Me.
Okay, I'm hot too. So, earthquakes, where do they happen?
On the ground.
What's the name of the place where they occur?
The Earth's
False.
crust.
Good.
The Earth's
Volcanoes, where do they typically happen?
in the magma.
Usually at fault lines, sometimes at hot spots. We'll get into that. So if you notice the top of 211, I've given you a map. I posted one a few weeks ago for those of y'all who were at home, and you guys were supposed to. What's up? Your teacher assistant? That means you get to go to my prep room over there and hang out and do your homework and whatever. Okay. Right. Close that door if you will. Thanks. Okay. So, and 211 at the bottom, you see our plates. At the top of 211, you can see the major plates on Earth. And so all these plates are moving around in some form or fashion. You can see there's arrows showing the direction of the movement that's taking place. And within each one of those plates, there's a bunch of little cracks and fissures, smaller faults. So where earthquakes can happen within the larger plates. But the main earthquakes and volcanoes are going to happen on the plate boundaries. Okay? All right, turn over to page 213. So the first one you've got listed in the notes are convergent plate boundaries. Convergent means what, Andrew? Converge. Come together. Thank you, Miss Beadle. So convergent, come together. Now, on Friday, you guys were supposed to watch the video, Japan's Killer Quake, and it talked about how the Pacific plate is moving under the Eurasian plate, and as it does so, it pulls that plate down, and eventually it puts so much pressure on that plate it springs back up. And as it sprung back up in 2010 in Japan, it sprung back up underwater, and all the area where it pushed that water up and out and displaced it, causing a tsunami. Yeah, so the earthquake was the movement of the earth, but the tsunami was the displaced water that moved out. Now, it's my understanding yesterday there was an earthquake in Alaska, 7.5-ish, and a tsunami warning. Maybe a tsunami happened. I didn't get that far. You might read up on that? I'm sure it wasn't on your Snapchat feed. Try looking at the news every once in a while, Trent. Come on. How many hours a day you spend on Snapchat? Snapchat's the devil. Okay. You on the internet, you heard me. Hope Snapchat doesn't sue me. So, let's see here. What was I talking about? Oh, convergent boundaries. So, convergent means they're coming together. So, essentially, you're losing land. One's going under another, you're losing land, right? So, where's the other land? How are we losing land all the time? At convergent boundaries, we can be, but that also means that new land is being formed in other locations. Now, there's another thing that can happen with convergent boundaries. Flip over to 214. So we talked about it, what's going on underwater. If you've got a lot of crust above ground and you've got a plate slipping under another one, then what happens to all that crust above it as one gets pushed, pulled, or slides under another one? I guess best way to put it. The crust, yeah, it's still getting crammed together and it's going to rise up, and that's how you have mountain ranges form. So if you look at 214 at the top, this is the Himalayan mountains, the simulation of that, where you have one part of the mantle slipping under the other, and the upper mantle, and then the crust kind of gets all pushed together, and that's how mountain ranges form as they get pushed up. the Himalayan mountains, basically India, you can think a long time ago was out in the middle of the Indian Ocean, and it kept moving toward Asia and got shoved up against Asia, and then the mountains formed. For all you on the internet, this is very technical. You're welcome. So that is convergent boundaries. So a couple different things that could happen at the convergent boundaries. Divergent. What does divergent mean? Turn back to 213. Separate. So they're separating, they're pulling apart. Now, if you look on the map over there, you'll see kind of a wispy white line down the middle of the Atlantic. If you look in your book on 211, you'll see the fault lines that run down the middle of the Atlantic. That is where your major divergent boundary is. So basically, the entire Atlantic there is just pulling apart. So, Jason, when you have two plates and they pull apart, what's left in the gap? Okay, so you would expect what to happen? Lava to come up. Yeah, so keep in mind, under the crust, you have all of this magma and it's hot. What happens when you have something really hot? What's it try to do? It's rising, it's expanding. And so when you have a crack that forms, you have lava and gases and stuff that are going to come up, and they're going to, basically what happens is it makes a little hump where it comes up, and it hardens because the seawater's cool, and so it's going to cool down and form new rock, and then it's going to split again as it moves apart. And so basically if you're like in the middle of the Atlantic and you were to go down and look, you'd see like a series of ridges. As it's pulled apart, lava's come up, it's formed a little ridge, pulled apart again, formed another one, and you just have a bunch of continuous ones as it keeps getting pulled farther and farther apart. We're getting closer and closer to where all the time? Asia. So we're moving toward Asia at about an inch or two a year, something like that. And we're getting farther and farther away from Europe and Africa. And it's probably well noted, and y'all probably seen this on a map, that the North America and South America fit pretty nice and neatly into Europe and Africa. And so it's thought a long time ago, they started diverging, and eventually we've got to this point where we are today. There's a lot of evidence for similarities between the South American East Coast and the African West Coast with fossils and different rock structures and stuff like that. Also has added scientific evidence for that. All right, and then transform boundaries, page 213. Transform faults are where you basically have two plates and they're just sliding past one another, okay? So the one you guys would be most familiar with or probably heard of is the San Andreas Fault in California on 214. If you'll look, I assume they took this maybe after a earthquake here. Basically what's happened is the plates have slid, it's pushed up a lot of sand and rock in that area, and you can actually see where that fault line is located in the middle of the desert when that happens. I don't think you guys there's been a big earthquake in California since y'all been alive. Not that I can remember, not a big one. There was a fairly large earthquake in Los Angeles when I was younger, and the San Francisco earthquake in, I want to say, 89 that happened during the World Series. But there hasn't been a big one since, so who knows? Probably at some point, I would expect soon that there's be some type of large earthquake in that area, something they're always prepared for. Okay, so that's a different type where they're sliding past one another. Let's see. Next Tuesday or Wednesday, we'll be going to actually, I'm getting the Mac cart. We'll have the computers in here, and we're going to work through an earthquake lab. So you guys, when you watched the video the other day of the Japan's killer quake, y'all noticed that, there's an epicenter where the main activity takes place, and then the energy spreads out. So in order to figure out where the epicenter is, you have to have seismic stations all over. And basically what you do is you triangulate, you use those three seismic stations to basically mark little circles to figure out where the center of that earthquake is. And so you guys are going to use some scientific information and data from real earthquakes and figure out where, how to triangulate where earthquakes start, and discuss the two main waves. And so hopefully that'll give you a better idea of how earthquakes where they start, where they happen, how it's measured, how scientists go about figuring that out. All right, it says, next thing to note, graph and plot major earthquakes and volcanoes, ring of fire. There's a worksheet I have for this, so you don't have to do this on your own. If you'll notice on page 215 here, where is most of the volcanic activity on Earth? In the ring of fire, which is around the Pacific Rim. You'll see all those little volcanoes, the little red arrows. So that's where the ring of fire is. That's where most volcanic activity. Now you see volcanoes all throughout. There's some shown in Southern Europe and Mediterranean, the Middle East, and some. Really, Africa has a ton of them down the middle. I think they call that the Great Rift Valley. There's a lot of geologic activity down that kind of. It splits Africa on the eastern coast. Lots of volcanoes and stuff going on there. And then, as far as the United States goes, the last time we've had an earthquake erupt in the continental United States was when? Mount St. Helens, good, which happened in 1980, before I was born. I think it was in June, July, somewhere in there. So that's the last time we've had a volcanic eruption in the continental U.S. Now, there's eruptions in Alaska all the time. There's eruptions in Central America. I actually saw a volcano erupting in Costa Rica in, 4 or 5. It was a very small one. It's actually one where basically like every 12 minutes there's an eruption and it spits out a little lava, and then it cools down and pressure builds up and it does it again. But a large volcanic eruption like Mount St. Helens, those don't happen too often. Hawaii has a continuous amount of volcanic activity on the Big Island, and that's actually what I want to look at next. Turn to page 213. So on 213, the next thing in your notes says island arcs. An arc is a what? Yeah, it's like a curve. Okay, so we're just going, don't get too carried away with the actual term. So it's just a curve. And you'll notice the Hawaiian Islands on 213, they form an arc out in the middle of the Pacific. So which way did we say the Pacific is moving? You're going east or west? It's going west. So if that's the case, the Hawaiian Islands, which ones are the oldest? Look on there. The ones on the left. Basically what's happening is there's a thing called a hotspot, which is a very zone, it's a zone of like a lot of volcanic activity and heat and magma that's up close to the crust. And as the plate moves over this hotspot, then volcanic material comes up and it forms an island. And the plate moves some more, and then it forms another island, and it keeps moving in that direction. That's why all the older volcanic islands on Hawaii are all far to the west, and the ones on the southeast, those are the new ones. Has anybody been to Hawaii in here? You went? Oh yeah, Cassie told me. Y'all didn't see the one. Did y'all see the volcano erupting? Well, you got to go back. So there's one new island forming. Lohi, I don't know how you pronounce that, but anyway, it's a new island forming. It's still underwater, and then it will eventually come up and be a new island soon. But the Big Island there on the south eastern part, it's still erupting now. It's not your typical like conical volcano like Mount St. Helens that looks like a mountain and the top blows off and volcanic material goes everywhere. The Big Island is basically what you've got erupting now is a caldera, which is just like an opening in the earth where just lava is constantly flowing out. And so it's been flowing out for 20, 30 years. I can't remember how long. It's been a long time where it's just a constant flow of lava. If you go to the southern tip, you can drive down to the southern point of Hawaii and you'll see it like steaming, lava flowing out in the ocean, and new rock, new land forming at that point. And that's still going on to this day. But that hot spot is the area just where it's really hot and a lot of magma comes up close to the surface, and as the plate moves over that hot spot, then that lava and stuff comes up, and that's where those islands are formed. Let's see. Faults. All right, let's look at 215. Okay. So, in the United States, we are all pretty much on one large plate there. You can see there's the United States and the part of the Atlantic. We're all kind of part of one plate. Actually, turn back to 211 because it names it. What plate are we on? The North American plate. So, can you have large earthquakes in the middle of a plate? Yes, you can. It's rare. Normally, most of your large earthquakes and volcanoes happen on the plate boundaries because those are cracks and there's areas where there's a lot of slippage taking place. And that's also like if you have lava underneath and there's a crack or a slip, that's where a lot of lava comes up. That makes sense. But in the middle of North America, in southeast Missouri, which is really almost like right in the middle of the United States, there is a large fault or crack called the New Madrid Fault, and there was a large earthquake back in the late 1800s. That was before they had seismographs, but the folklore says that the Mississippi River ran backwards for a while because the geologic disturbance, new lakes and stuff were formed because it moved the land so much. I want to say that people were reporting like the church bells ringing, and as far as away as Pennsylvania. Like this was a massive earthquake, probably close to high 8s, or like maybe even 9, right in the middle of the United States. Yes, it would have been felt here basically, and Missouri's pretty far away. So then that could very well happen again. I mean, it's been a while since that's taken place. So, Andrew, are you awake? Yeah. Wake up. So, any questions about earthquakes and volcanoes? What causes earthquakes? When they move. Yeah, so we actually, and I was going to say this, I saw James Spann had posted, we had a earthquake in close to Fayette, if y'all know where that is, about 45 minutes north of here. 2 or 3 days ago, I think it was like a 2.8. So it's a pretty small one. I'm sure you'd probably have been right on top of it to feel it. But there are small faults all throughout the different plates where earthquakes can happen, where the rocks can shift and they can move. I told y'all about the one my parents were in, right? No? So my parents live in North Alabama, about an hour and a half north of here, and where I grew up. And probably 10 or 15 years ago, there was an earthquake there. I think it was like a low 4. And I called my parents, and they were like, "Yeah, it sounded like somebody was on the roof." This is like 4 in the morning. My dad said he woke up. They woke up, and it sounded like somebody was jumping around on the roof of the house. So it wound up. He got up and didn't see anything. I don't know. No telling what he thought was going on, because I mean that's not something you normally think of happening around here. The next day, went outside, and like the bricks on the back side of our house had a huge crack all the way down the side where it had shaken the frame enough where it cracked those bricks loose, and you had to go back and fix all that. So we can't have earthquakes around here. Most of the ones in Alabama, though, are in northern Alabama. There's not quite as many this far south as we are. Okay, and like I said, we're going to do the web quest, but we'll do that online. Skip down to soil. Real quick, we're going to go through these first 3 things on soil, and then we'll get to the lab, and you guys can work as much as y'all need to get through parts 2 and 3, hopefully. Although it seemed like yesterday you guys were a little more efficient than some of the other groups. Turn over to page 221. Quinte, tell us what soil is.
Soil is a mix of geologic and organic components.
Keep going.
Soil forms a dynamic membrane that covers much of the Earth's land surface, connecting the overlying biology to the underlying geology.
Okay, so it says a mix of geologic and organic components. Geologic means like broken down rock material, so that's your minerals and stuff in the soil. Sand, silt, and clay is the 3 primary ones. We're actually going to do a soil lab toward the end of this week, first of next week, so you can determine components. And the organic components, Jeremiah, what does that mean?
Stuff like plants.
Okay, that's dead material, usually plants that's been broken down in the soil. Okay, which also adds lots of nutrients to the soil and improves the quality of soil. Why is soil important, Colby?
It helps plants grow, like live plants.
Yeah, so if you don't have good soil, you can't grow plants, and we need plants to grow food. Now, why is this all important? Because it sounds super boring, right? Well, the next unit we're going to get into is we're going to be like feeding the world, sustainability through how we produce food and agriculture. And so soil is kind of the foundation of that because there's kind of this new ethic. Back in the day, it was most farmers would be like, feed the plants, they'll grow, that's what we eat. But now there's a lot of people who are like, if you feed the soil, then the soil will feed the plants, and then the plants will feed us. So the better soil you have, the better food production you're going to have overall, and the healthier ecosystems you're going to have. Okay? So that's why we're going into soil and why it's important, and also because it's on the AP exam. So keep that in mind. So soil, where we grow food. Where is the best soil in the world found?
Tropical rain.
What, let me rephrase that. What, Layla, what biome has the best soil?
Tropical rain.
No! Tropical rainforest, what's the soil like there, Luke? It's horrible. Why is the soil in the tropical rainforest bad?
Because all the nutrients are used up.
Yeah, there's a very quick organic breakdown of materials, and so what happens is the plants in the rainforest absorb those nutrients really quickly. So it's kind of contrary to what we would normally think with all the biodiversity and stuff growing there. The soil tends to be pretty bad, which is an issue when you start slashing and burning the rainforest, because then you don't have very good soil for growing stuff, and that's happening a lot in the rainforest. But the best soil in the world, Caleb, is what? Located where? We went over this. DeQuinte?
Is it in the temperate?
Jordan? What? Which kind of forest? I mean, we have pretty good soil here, but that's not the best soil. Jemiah? We went over this. Who knows? Grasslands. Grasslands have the best soil. They have the best, deepest topsoil. Savannah, yeah, would have good. Like our grasslands in the Midwest would have the best soil in the U.S. And then like in Europe, there's a lot of like large grasslands that have really good topsoil. Savannah, I would imagine, would have pretty good too. Basically, what happens is the grasses break down over time. They build up. There's a lot of fires. The grasses regenerate, and they just can kind of continually build up over time. A lot of places you'll find, like if you were to dig down topsoil, like good rich topsoil that may be 5 to 10 feet deep, whereas our topsoil around here, we're lucky if it's 6 or 8 inches deep if it hasn't been scraped off by somebody building a neighborhood. So good soil leads to good food production. Okay, and we'll get more into that in the next unit. Weathering. Turn to page 219. Rachel, what is weathering? Wuthering Heights. Quick, who's the author? Charlotte or Emily Bronte? I can't ever remember.
I think it's Emily.
I think it is Emily.
Weathering.
Yeah,
Something about rocks.
Isn't that where like rocks are slowly breaking down?
Yeah.
Is your name Rachel Donovan?
That's-
Rachel, what's weathering?
I just said that.
What'd you say?
Rocks.
What about?
Break it down.
Okay, so that's the simple version. Rocks breaking down. What are the two types of weathering? Physical and. Well, okay, Jason, describe physical. What are some? How would you physically weather rocks?
How would we do it?
I mean, no, I mean just in nature.
Oh, I mean, usually like they're exposed to like heat or pressure.
Heat, pressure, mostly wind, probably more wind and water. Don't start me on erosion yet. We're not there. What'd you say?
Oh, I just said water.
Yeah. So like wind and water, cool and heat. Yeah, that can work, Jason, especially if you're talking about like freezing and cracking and stuff. So those are all components of weathering. That's physical weathering. Chemical weathering, Jemiah, would be what? Chemical reaction. So flip over to the next page, 219. If we'd had a normal year, we probably already went on a few field trips, and hopefully in the spring we'll get to go on some. And one field trip I really like to do is there's a cave system in northeast Alabama, and it's spectacular. And so caves are formed via chemical weathering. So basically what happens when it rains, carbon dioxide in the air gets dissolved in the rain. Carbon dioxide in water forms what? Carbonic acid, just like in your drinks. You drink a soft drink, it's got carbon dioxide in there. It's really acidic. It's from carbonic acid, okay, as it disassociates in there. So that carbonic acid then runs through the soil, and if it runs through limestone, it forms caves. And so you have lots of cave systems formed from that acidic breakdown of that rock. Good. And hopefully, like I said, hopefully we'll get to go see something like that in the springtime. Maybe we'll get to go camping. Who knows what we'll get into if they lift this field trip ban that we've got. Erosion. Now, contrast erosion to weathering for us, Andrew. Donovan, what do you think erosion is?
Is it erosion? It's like the form of water, land water, breaking up particles of rocks from like rain or like.
How is it? So weathering, we said, is the breakdown of rocks.
Building of
Erosion is the building of rocks.
No.
Luke, Layla,
The removal.
the removal. Okay, so for those of you who are looking on 220, where it actually says erosion in bold terms, the physical removal of rock fragments, sediment, soil, rock, and other particles. So weathering breaks it down. Erosion moves it away from there. Wind, water, people. Now, why is erosion significant?
It can cause landslide.
Okay, Fleetwood Mac. So erosion's really bad because the number one pollutant in aquatic systems in the world, freshwater aquatic systems, is sediment. Okay? So when you have lots of erosion and sediment gets into the water, causes a lot of stuff to die. Thanks, Mom.
Thank you.
Caleb, congratulations. Rachel, get it. Good catch. All right. So, erosion, bad. Any questions?